All right, so welcome back. Over the last 2 weeks that we have in class, we'll go ahead and finish up with searching and sorting. Remember that the last 2 weeks of lab and hack are your opportunity to come in and demonstrate a reworked hack, reworked one lab, and we'll go ahead and regrade those live in front of you. Otherwise, there's no more attendance points to go. Your last reading was yesterday. You only have one more hack, and then of course the final exam. More details on that will be posted either later in the week or next week. But it will definitely be asynchronous. You'll have another 24 hours rather than just the 2 hours that you've been allotted. It will also have I think 20 questions that are multiple choice questions. And then you'll also have some actual programming to go along with it. All right. Any questions now that we're back? No. Otherwise, we left it off talking about binary search, right? That you have an array and that you want to search that array. Linear search allows you to do that, but it requires a linear amount of time. So that if you go from 1 million integers up to 2 million integers, it's going to take you twice as long. But binary search, you can do a lot better. In fact, you can do exponentially better, right, from our analysis that we ran through right before the break. The idea is that you exploit the fact that it's sorted. All you have to do is look at the middle element. And if that's the thing that you're looking for, great, you're done, right? Otherwise, if the thing that you're looking for is smaller than that element, then you search in the left half of the list. Otherwise, if it's greater, then you search in the right half of the list. In either case, you've cut it in half. And if you do that continuously, recursively, or iteratively, you're cutting it in half, cutting it in half, cutting it in half. That leads to a logarithmic number of comparisons instead of a linear number of comparisons, which is why it's so essential that's a huge speed up, right? The problem is, of course, that it requires that the array be sorted. And that's what we're going to that's what we're going to focus on now, right? We're going to turn our attention to sorting algorithms. Right? We didn't do it last time here, but how would you go about sorting this array right here? Let me go ahead and copy it so that I don't lose the original, right? How would you go about sorting this? Oh, okay. So you want to go backwards, look for the biggest element and put it at the end. Let me go ahead and switch that, and let's look for the smallest element and put it at the beginning. Right? The same idea. It's just that we're going to work left to right because that's how I read. I read left to right. Right? So I'm going to, and it's in ascending order. Right? Of course, we could also sort it in descending order, in which case we would take the maximum element and then put it at the front instead. So I'm going to go ahead and go through this. 4, that's not the minimum because I found 2 later on. 9 is greater. That's not less than 2 that I found so far. 4 is not less than 2 that I've found so far. 1 is less than 2, so there's the minimum that I've sought so far. 3 and 10, they're not less than 1. So what am I going to do? Swap 1 and what was in the front? 4. There we go. Excellent. And then get rid of that redundant 1 there. Now, do it again. But are you going to consider this first element that you just put where it belongs? No. You're going to consider all of the other elements over here. Okay? And the way that you're going to go through and you're going to find the minimum among them, right? So 8, or I'll start out with 8. Okay, I found 2, that's even less, right? 9 is not less, 4, 3, 10. And so I end up swapping 2 and 8. Right? And I'm going to continue on that, right? So let's go ahead and try to generalize that with that array, okay? Think of this not as an array, as the array that we had here. But think of it more, actually, let's start out with this actual array first, right? So let's think of this in terms of iterations. The first iteration, okay? On the first iteration, I'm going to search among elements 0 through, and I am going to generalize this a little bit right now and just say that this is n minus 1. These are indices, right? Among indices 0 through n minus 1, where n is the size of the array, right? That's the number of things in the array. So I'm going to search all those elements for the minimum, And in this case, it was 2, right? And so I'm going to keep track of that as well. And now what do? I swap the minimum and the well, here, I'll write it like this. I'll swap elements. which elements do I swap on the first iteration here? The element at index 0, and in this case, the element at index 2, right? This is the minimum, okay? Now think about iteration 2 after I've done this. When after I've done this, then 4 and 2 have been swapped, 4 and 2, and what I'm going to do is I'm going to color in that first element because it's sorted. We're done with it. We're never going to oh, wait, what am I doing, right? Was that the minimum element? No. I'm thinking from the example from yesterday. 1 and 4. There we go. 1 and 4. There. That's sorted, and that one is there. So that was not at 2. That was at 5, 1 at index 5. Right? So here we're swapping 0 and 1 at index 5. There we go. Okay. Now on the second iteration, I am not going to consider all the elements 0 through n minus 1 on the indices. Instead, what am I going to search? 1 through n minus 1. I still do go all the way to the end here because this could end up being like 0 or something, and that needs to belong, or it could that could be 2, and that needs to belong right over there or something. Okay? So I search for the minimum. In this case, which one is the minimum among these elements? 2 at 2. 2 at 2. Right? And so I end up swapping the index 1 and the element 2, index 2. Okay? And so 8 and 2 here are swapped. And at this point, the second one is sorted as well. Right? So let's go ahead and fast forward here. In iteration 3, I'm going to consider 2 through n minus 1. And I'm going to find the, whatever the minimum is here. And in general, I'm going to swap the minimum and index what? In the third iteration here, 0, 1, and 2, right? Now, the thing to realize here is that this index right here is going to match this index right here. In other words, if you are sorting this sub-array right here, where are you going to put your minimum? Well, wherever you start. So now let's generalize this. Dot, dot, dot. At index, say, I. I don't want to do that because I'm off by 1. But so at some index here, and I'll go ahead and fill that in. I'm going to go ahead and search from I up to n minus 1. And I'm going to search for the minimum, wherever that might be, and I will swap whatever the minimum index is and I. Right? Now, when do I end? When do I stop? How many iterations do I go? n minus 1, good, why? So let's fast forward here. What is it going to look like? 8, 9, 4, 4, 3. So this is going to end up looking like 3, 4, 4, 8, 9, was it? 8, 9. And at that point, what I've done is I have sorted everything up to and including the second to last one. Right? Do I go one more iteration to sort this guy? Why? He's already where he needs to be. Right? If you've sorted the first 8 or 7 of these things and you've put them all where they belong, then that last person, that last one at the end, it's already there. So you don't need to go n iterations. You don't need to sort n things. You only need to sort the first n minus 1 of them. That tells me what should I write my on the second to last iteration here. Where am I going to go? I'm going to go n minus 2 up to n minus 1. Right? I'm going to find the minimum, and I'm going to swap with the min index, and I in this case is n minus 2. Right? Now writing it out like this, and generalizing it, and placing in variable values for each one of these values that ends up getting changed, that helps me write my actual loop when I go to implement this thing. Now this thing is called selection sort. Why is it called selection sort? Because each time you're going through and you're selecting the minimum and you're putting it at the front where it belongs. Right? So let's go ahead and call it selection sort. Selection sort. Right? It's not going to return anything. Instead, you're going to give it an array, and it's going to rearrange the array so that it's sorted in ascending order. That means that it has to take an array as input. Const int star array. Is that going to work by placing a const in front of it? Am I going to be able to swap these elements? Nope. So we're actually going to be making changes here to an array for once, and we're advertising that fact with the explicit or the implicit omission of that const keyword. What else do I need to tell the function? How big it is. In this case, I'll just say n. Right? All right. So let's go ahead and write the for loop here to do this iteration. We're going to run for I, running from 0, 1, 2, dot, 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 and minus 2. Okay? So it's not going to be an idiomatic for loop. For int I equals 0, I is less than n, I plus plus. Come on, I plus plus. That's an idiomatic for loop. I'm not going to go all the way to the end, though, am I? I'm going to go one less, because that last guy is already sorted. Now, it's not going to make a difference on the correctness. It'll still be correct. All you'll end up doing is taking that last element 10, realizing that that's the minimum, and then swapping it with itself. It's kind of a useless operation that we're going to omit by not going all the way to the end. Okay. Now, my first step is here is to find the minimum among elements array sub I through array sub n minus 1. Right. The ith element all the way to the end. Find the minimum, and where do you put it? At the ith element, or at index I. Swap the minimum element with the element at index or at array sub I. There we go. All right. So help me out with this first one here. I need to find the minimum among all those elements. What kind of a what should I do to do that? Another loop. For int. Can I use I again? Nope. That's being used in the outer for loop. So what comes next? J. Where should I start it? Where should I end it? J is less than or equal to something, J plus plus. Right. Right. So if I'm going to find if I'm going to search elements I through n minus 1, where should J start? 1. I through n minus 1, I should just start at maybe I. Right? Except, let's not lose the forest for the trees here. What am I trying to do? I'm trying to find the minimum. Right? To keep track of that, I should probably keep track of a min index. And now where should I start that min index? If I'm going to be searching elements in general, if I'm going to be searching elements I through n minus 1. We'll go ahead and assume that that first guy that we see is the minimum element, and then go through the rest, and if we find something less, we'll update the minimum element, etc. Right? So I'll start it at I. Now, do we need to rethink that? Should I be comparing the element at I to itself? No. Why? Start at I plus 1 so that you're comparing the ith element to the next one, then the next one, then the next one, then the next one. Right? So where do I stop? I need to go all the way to the end. N minus 1? Careful. That's a strictly less than, so what should this be? Or I could change it so that it's less than or equal to, right? Or I could just say n less than or equal to n, right? Achieves the same thing. This one is a little bit more idiomatic, right? All right. Now, if the element at the min index, or if the ith element is less than the element that we found so far that's minimum, then we need to update our index. Min index is equal to I. Oops. Are those correct? Nope. So what should I be comparing to? What is this loop being controlled on? J, right? So J, and then it gets updated to J. There we go. At that point, we've found the minimum element at min index. We need to swap the minimum element with the ith element. So Let's go ahead and create a temporary variable here. We'll take in the variable at I. That frees it up so that we can put in the variable at min index. Right? And then min index has been freed so that we can put in the variable temp. Right? There, that's it. It's a void function, so you don't have to return anything, but it's still best practice to have that return statement. All right. I've got a couple of method or functions that I put in here: print array, array, and n, and then we can call our selection sort array on n, and then we can call our print array again to see that it actually worked. Okay, so I'm going to print it before I sort it. You'll see that it's going to look like this. I'll go ahead and call my selection sort algorithm, and then I'll print it. The print array, it's called print array, sorry, not print r. There we go, and there we go. Right. So if I had no bugs, it should actually run, right? Ignore those warnings from last time, right? There we go. So there's the original 4829 ... right? And there's the sorted. Is it indeed sorted? Looks like it to me. Okay. All right, well, no, that's not what I wanted as sorting. What I wanted in sorting, I wanted to go in descending order. I wanted 10, 9, 8, 4, 4, 3, 2, 1. Okay. What would you change in this algorithm to achieve that? Oh, you could go ahead and reverse everything, all right? I'm thinking about a minimum change among this code, though. Yeah, that's all you need to change it. All right, let's go ahead and change it back. What if instead of integers, I was sorting books instead? Right, we looked at books before, old. Yeah, what is a book? A book is a title, an author, a rating, a release date. What does it mean to sort books, though? How would you sort a book? Author's last name? So author, last name, first name. Okay. Is that the only way? No. Rating? Up or down? All right, ascending or descending? Which one do you want? Right. Everything. Right? I want all of this stuff, right? So am I going to cut and paste this entire function just so that I change one line of code when I want to sort something different, or I want to sort it in a different order? Probably not. That's not the way to go. Right? But until then, we're not there yet. All right? So let me go ahead and restore this. Array of j is less than array sub min index was the original, right? And now I've restored it. Before we even get there, though, what I want to do is I want to test and see if this not only does it work, but is it a good algorithm, right? Now, is it a good algorithm, meaning that I'm going to go ahead, instead of creating an array here, I'm going to go ahead and create a new array. Int array is equal to, I think I've got a random array here. There we go. A random array of, say, 10 elements, right? And I'll go ahead and put in n here, 10. There we go. There. Now, each time I run this, it's going to run it on a different test case, right? Is it indeed sorted? Yeah. So not only did it work on that original static fixed test case, but it works on this dynamic test case that I can go ahead and check it out. Oops, sorry. Forgot to seed the random number generator. srand time null. There we go. Otherwise, it's always going to produce the exact same sequence of random numbers. There we go. Now it's going to be different every single time I run it because it's going to seed it based on the current system time. Right? Well, okay. So if I'm too quick about it, then it's going to use the same exact second or microsecond or whatever it is, thousandth of a second. But if I do it several times here, ooh, 3 18s, wow. 6, ... right? By randomly generating input, right, I've got a lot of test cases. In fact, all I have to do is keep doing this over and over again, and I've got another test case, another test case, another test case. Right? Excellent. what if does it sort really large arrays? Right? Well, first of all, is 100 really large? No. Right? So let's find out if it sorts really large arrays. Okay, 2, 2, 0, dot, dot, dot. Well, now it becomes visually daunting to examine this stuff visually. So at that point, I would probably program it. But I also want to know, is it efficient? Okay. So to do that, I'm going to go ahead and get rid of the print statements because I'm going to make this even larger. And I don't want to see the output because I'm not going to be able to verify 1,000 different numbers here. Okay. GCC and run it. It was pretty quick, right? It was a blink of an eye. In fact, it was so fast that I'm going to have to use a utility here to time it. Time a.out. It took 0.004 seconds of real time to get that done. Right? Or system time here, 0.003 seconds. All right. Well, if it's a larger input, obviously it's going to be slower. Right? If I go up to 10,000, then it's going to start to become noticeable. Right? Now it's a fraction of a second, like an eighth of a second or so. 0.12. What if I went up to, say, from 10,000 to 2,000? Or 10,000 to 20,000. I doubled it. Right? Make your prediction. Remember, before it was doing about an eighth of a second here, 0.12 seconds. Now, if I double the input size, and it's kind of like linear search, then it would double the time it takes, right? But it takes way more. Right? What is that? Before it was 0.12. Now it's 4 times as big. Right? What if I went up an order of magnitude instead? Remember that 10,000 was 0.12 seconds. What if I go up to 100,000? Now it becomes super noticeable. Is 100,000 integers all that much? That's 100K, 100 kilobytes. Right? And yet it takes 10 seconds or almost 12 seconds there. In other words, 100 times slower. Right? So let's see if that pattern holds. If I go up to 1,000,000 and it's 100 times slower, how long will it take now? Remember, it was 12 seconds before. 100 times 12 seconds is 100 times 12 is going to be 1,200 seconds. 1,200 seconds is 20 minutes. Right? So let's wait for that and understand why. Right? So what I'm going to do is I'm going to copy down just the pseudocode for a selection sort. Remember that we had this outer for loop that ran from I, running from 0 up to n minus 2. And I'm going to be inclusive on both of these ends here. It's inclusive on 0 and inclusive on n minus 2. And then we had another inner for loop here that ran j from I plus 1 up to n minus 1, inclusive on both ends. And then within that loop, we were doing something. Do something. What was that something? Here's the inner for loop. Here's that something. So there are essentially two lines here. There's a line on 65 and a line on 66. Is 66 always executed? No, why? If the if statement is false, this does not get executed. Line 65, is that always executed? Yes. And what is it doing? Just like linear search, just like binary search, it's doing a comparison. Right? So what is that something? It's comparing things. Compare. Array sub j and array sub min index. Okay. So now what I want to do is I want to answer the question of how many total number of comparisons are made in total with this pseudocode right here. I'm going to move it down to give myself some more room. Okay? Well, we're going to go ahead and look at this from the inner part to the outer part. Let's just go ahead and concentrate on line 3 for now. On line 3, how many comparisons are made? Good. How many comparisons? 1. right? If you just look at line 3, right? There's only one comparison here. Right? Now, the question becomes, how many times is this box executed with respect to this for loop on the outside? Right? So I'm increasing my attention here to this block of code here. Right? How many times do we execute this box within this box? We execute it when j is I plus 1, I plus 2, I plus 3, dot, 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 until j is n minus 1. How many ones is that? Right? So 1 for I, be I plus 1, plus I plus 2, plus I plus 3, plus dot, dot, dot. We go up to and include n minus 1, plus 1 for n minus 1. So how many are there here? Oops, that's terrible. There we go, that's better. What's the total? Would it help if I wrote it out like this instead? 1 plus 1 plus dot, 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 plus 1. If I started out at 1, 2, 3, plus dot, 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 can you answer the question of how many there are total now? N minus 1, right? N minus 1 ones. Now, how many are there here in this section? If I only go up to I. There are I of them. So if you have a total number of all of these, and you're not counting these I of them, how many, what's the total now? N minus I minus 1. I like that, the way even the way that you put it. That you put the I, you didn't put the, you switched out the I and the 1 here. Good. So n minus I minus 1. So n minus I minus 1. Now, what about the last box here? Because that's the final answer, right? How many times is that inner box, which executes that many times, executed with respect to this outer for loop? Yeah, go ahead. Something like that. We'll get to it, though, right? We still need to do the math to get there, though, right? So for this one, I'm going to go ahead and set up a summation. And hopefully, oops, that's not what I want. Right there. There we go. All right. We've seen summation, sigma summation notation before, yeah, right? Well, that's even way before calculus, isn't it? All right, so I'm running I from 0 up to n minus 2. And what I'm doing is I'm summing n minus I minus 1 every single time. Okay? Move this over. Now help me out here. How could I break that up? How many sums are inside here? This is actually n plus negative I plus negative 1. Right? I've got 3 sums here so that I can split this summation up into sums. I is equal to 0 up to n minus 2 of n minus, and I'm immediately just pulling out the negation out front, I is equal to 0 up to n minus 2 of I minus summation of I equals 0 up to 2 minus n minus 2 of 1. Right? Summation of sums is equal to the sum of summations. Okay? Now, this one and this one should be pretty straightforward. This is n plus n plus n plus n. How many times? Careful, don't just answer n minus 1 or minus 2. Where do you start? 0. So if I go from 0 up to n minus 2, how many things am I actually doing? N minus 1. And each time you're adding in n, so it's n minus 1 times n. Right? I don't know how to do this second one yet, so we'll leave that off for a second. But I do know how to do that last one. That's just the same answer, 1 plus 1 plus 1 plus 1. Again, how many times? You start at 0 and you go up to n minus 2. So this is 1 times n minus 1. We don't write it like that, though. How do we write it? N minus 1. Okay? Now we do need to focus on this summation right here. To do that, I'm going to tell you a story about this guy named Gauss. Right? So again, this is probably an apocryphal story, but and in fact, I'm pretty sure it's apocryphal. But the story goes that Gauss was a young boy and he was bugging his teacher, and so the teacher gave him some busy work to do and said, "Go off into the corner and sum up the numbers 1 to 100." Thinking that it would take him a long time to do it, right? Because it's grunt work, it's busy work, right? He came back immediately with an answer of 5,050. How did he do it? He came up with Gauss's formula. The sum of natural numbers, 1 plus 2 plus 3 plus 4 plus ... plus n, has a closed form solution that is n times n plus 1 over 2. Right? So plug in 100 for n, and that's what he was asked to solve. 1 plus 2 plus 3 ... plus 100. What do you get? 100 times 99. Divide that 100 by 50, or by 2, you get 50. 50 times 99 is 50, isn't it? Yeah. Say what? Oh, was he asked to do 101? No, it's thank duh. 50 times 101, right? 50 times 101, 50. There we go. Thank you. All right. So that's Gauss's formula. You don't have to commit it to memory, but you eventually will, because if you're doing a lot of algorithm analysis, right? This comes up all the time. Why? Because you've got a for loop within a for loop, right? And that inner for loop is usually based on the outer for loop or some combination thereof. And so you get something that looks like Gauss's formula a lot. This is not exactly Gauss's formula here. Why? Do we start at 1? Nope. But if you start at 0 plus 1 plus 2 plus 3, what happens to that 0? It goes away. Right? So let's go ahead and change that to 1 immediately. It looks more like Gauss's formula now. But it doesn't go all the way up to n. It goes to n minus 2. So what I could do is plug in n minus 2 for n, right? Plus 1. And what happens? Right? It's n minus 2 times n minus 2 plus 1. That becomes n minus 1. So don't lose the other terms here. This becomes n minus 2 times n minus 1 all over 2 minus n minus 1. Right? At that point, it's just algebra, ... Right? In fact, I don't even want to do it. At that point, I'll ask Wolfram Alpha to do my work for me. Right? 9n times n minus 1 minus n minus 2 n minus 1 divide by 2 minus n minus 1. There we go. And hopefully you'll simplify automatically. Nope. Okay, fine. Simplify, please. There we go. So 1/2 n times n minus 1. And I'm coming back over here. So credit to Wolfram Alpha there. Right? That's just basic algebra. Right? Let me expand this out though a little bit to the second one that it had. 1/2 n squared minus 1/2 n. Between these two terms, which one's more important? Again, let's not lose the forest for the trees here. What are we counting? We're counting the number of comparisons that are made by this selection sort algorithm, the amount of work that it's doing. As we grow our array here, right, n will get bigger and bigger and bigger. Note that it's still not done. Remember, I said it was going to take about 20 minutes, and we're going to see why here in a second. We don't sort small arrays all the time, right? Arrays grow, right? Data gets bigger and bigger and bigger, and that's what we're interested in with respect to the behavior. Right? So as n tends towards infinity, which one of these terms is more dominant? The n squared term or the linear term? N squared. So immediately, let's just go ahead and ignore this lower order term. Okay? Now, what about this 1/2 right here? Is that all that important? Remember that there's some hidden constant out front here that tells you how many seconds a comparison actually takes, right? It could be 2 microseconds. It could be 4 microseconds, right? You could have a very slow computer and it had to be 50 microseconds or something. You could take it and move it to a brand new computer, right, that is twice as fast, 10 times as fast, and this C changes again, right? So who cares? What I'm interested in is the highest order term involving n, right? This is about equal to n squared. Right? Now, let's go ahead and look at, or do a thought experiment here. The same thought experiments that we did before the break. I'll go ahead and explain them again, right? That if you have an input size of n, the time that it takes you, time or resources, or in this case, number of comparisons, is n squared. If you double the input size, like we were doing in our experiment here, what happens to your time? Now it's 2n squared. Use your algebra skills to figure that out. What's going to happen? You distribute the 2 and it becomes 4n squared. And so therefore, between these two, it's 4 times as much, right? In other words, 4 times slower, right? Does that truck with what we were observing? It went from 0.12 seconds to 0.48 seconds or 0.49 seconds. 0.4 seconds went to, what was it, a full second, right? What if we went from n to 10n? What's it going to look like now? What happens to that 10? No? Algebra is boring? All right. There we go. That's not even algebra, that's just arithmetic, right? So 100 times slower. Does that truck with what we were looking at? Right? It went from 0.1 seconds to a full 10 seconds or 12 seconds or whatever it was. And now we understand why this is going to take 20 minutes. It's 100 times slower. Before it was 12 seconds, now it's going to be 1200 seconds or 20 minutes. I'm not sitting around waiting for that, right? We went a full 15 minutes, so if we'd only waited like 4 more minutes, we could have seen it actually execute, right? But I prematurely killed it, okay? Say what? Yeah, I'm not going to sit around waiting for it, right? So, just as with linear search, we found a better way using binary search. Is there a better way that we can do sorting, right? So before we do that, though, let me go ahead and put in my notes here for selection sort. Remember that the basic idea here is that you go through the array, you select the minimum element, and then you put it at the front. Then you only have n minus 1 elements left to do. You find the minimum among that, and you put it at the front, right? This is a very inefficient way of doing it, but it's how humans would do it, right? And this is why it's one of the first sorting algorithms. Let's be better about it, right? I've got the same array here. What I'm going to do is I'm going to use the same idea as binary search, but I'm going to use, but I can't assume that it's already sorted. I'm going to use a divide and conquer approach. Binary search says, well, if it's already sorted, I can go ahead and jump in the middle, and then I've divided it into two parts that I can go ahead and search either this part or this part. I'm going to do the same thing, but with sorting. I'm going to take this first guy right here, and I'm going to call him a pivot element. All right? So 1, select the first element as a pivot element. So NCAA basketball has started. What is a pivot foot in basketball? Nobody follows basketball. Okay, so you land down on your pivot foot, right? And if you pick it up, it's traveling, right? If you're holding the ball. But what can you do with your pivot foot? You can pivot around it, right? You can, or an irrigation pivot, if you've ever seen those, right? It goes around a central point, right? We're going to do the same thing with this pivot element. We are going to partition all other elements elements around it. Smaller to the left, larger to the right. Right. So let's go through the rest of these. 8 is greater than 4, so I'm going to put it over here. Right. 2 is less than 4, so I'm going to put it over here. 9 is greater than 4, so I'm going to go ahead and put it over here to the right. Right. And then fast forward here. 4, you can break tires arbitrarily. I'll go ahead and put it onto the left. 1, 3, and 10. Now that I've pivoted around this, everything over here is less than 4. Everything over here is greater than 4, less than or equal to over here. Where should I put this pivot element now so that I don't lose it? In the middle. Just like binary search. But unlike binary search, where it is already sorted, we're in the process of sorting it. What do I do with the left and what do I do with the right? I do it again with the left. I do it again with the right. I never look at 4 again because it's where it needs to be. Right? Don't ever move it again. Right? So do your recursion here, right? You're recursing on this. I'm going to select the first element here as the pivot element, and then I'm going to pivot around it. So 4 is greater, 1 is less, 3 is greater. Guess where 2 ends up? Right there. And now tell me about that entire left sublist there. It's sorted, right? That was quick, wasn't it? Right? Let's do it again on the other side. 10, right? All right, well, 9 is less, so I'll go ahead and put 9 over here. 8 is less, so I'll put it over here. And then 10 gets put over here. And it's where it needs to be. I will recurse on this sublist and this sublist. But tell me about this sublist right here. It's empty, right? So by definition, an empty list or an empty array is sorted. By definition, a list of size 1 is sorted. That's your base condition. You stop when you've got an array of size 1 or an array of size 0, and you're done. Right? This one would actually recurse, and you'd actually see, okay, well, 3 here is a pivot element. 4 is greater, so it gets put on the right side, but then 3 gets put where it already is, and you end up with the same thing anyway. Right? That was really, really quick. Right? In fact, that's what it's called, quicksort. Right? Quicksort has a best or average runtime of n log n. Okay? So the analysis is beyond the scope of this course. You'd have to come up, you'd want to apply the master theorem and analysis of recursive algorithms, all that kind of stuff, right? I don't want to go through that, and instead of what I want to do is I want to cut to the chase and show you actually how to do this stuff in practice, right? We're going to use quicksort. We're not going to use selection sort or any of our own sorting algorithms at all. Instead, we are going to use what's built into the standard library. But I do want to look at how much better this is by going through those same thought experiments, right? If I go from n, and it requires n log n comparisons, right? And I double the input size, what happens to my performance? What happens to the behavior of my algorithm here? 2n log 2n. Right? So I'm going to break that up into 2. Tell me about that log 2n. You remember your log identities? Log AB is equal to log A plus log B. So I can split that up into log n plus log 2. What happens to this thing right here? Remember, it's implicitly base 2. So it's 1. There we go. So now I'll go ahead and distribute that 2n, log n, plus 2n. There we go. So, I mean, it's almost linear, right? We double the input size here. We double the number of comparisons that we make, except that we also add 2n comparisons, right? Again, I'm not worried about lower order terms. Let's go ahead and ignore that. And we can call this quasi, here, let me respell it. Quasi, no, that's not right either. There is a U in there. Quasi-linear. There we go. Tried to think of another word that had quasi in front of it, but I couldn't think of any. Quasi. That's what it means, almost. The only thing I could think of was Quasimodo, which is almost man, right? The Hunchback of Notre Dame, right? Quasi-linear. It is almost linear. It's nearly linear, right? In fact, if you ignore the lower order terms here, it is linear, right? Yeah, go ahead.
That's the number of comparisons still?
That's the number of comparisons. And again, if you ignore the lower order term here, it is linear. That's why we call it almost linear, right? In fact, when you go from n to 10n, what happens, right? Same thing happens, right? And I'll give myself some more room here. 10n log 10n, right, is equal to 10n log n. And then your additive factor down here is going to be, what is it, log base 2 of 10 times n. In other words, this factor right here just changes, right? But even that is taken down by a factor of, by a logarithmic factor, right? Log 2 of 10 is going to be 3 point something, 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 right? So, quasi-linear, it's still only going to be 10 times slower, right? Which is kind of like the behavior of linear search, but I mean, that's what you have to pay for, right? It's not free to sort things, right? Okay. Any questions so far? Because again, I don't want to implement these things myself, right? All I would end up doing is changing this one line. I would maybe change the variable names here instead of min. If you're doing in descending order, you'd want max instead, or that you would reverse everything or whatever. Ultimately, all you're doing is changing this one thing, right? So what I want to do is I want to introduce a different component, okay? So suppose that I have this generic sorting algorithm, right? Generic sorting algorithm, right? And it takes as input an array and everything else that you need, like the size of the array or whatever, right? And it outputs a sorted array. Sorted array, right? Now, what is this? Is this an array of integers? Is it an array of doubles? Is it an array of, say, books? Right? Yes, because it's generic, right? So if you receive, if you are a generic sorting algorithm here and you receive an array of integers, right, you know how to do that because you've got this built-in less than symbol, right? If you receive an array of doubles, you know how to do that as well. But if you receive an array of books and you have this A and this B, do you know if they go like this, or they're out of order and need to be swapped, or that they're equal, so leave them alone? Or if you're quicksort, right, you have this pivot element and then you're comparing it to this other element over here. Does it go on the left side or does it go on the right side, right? So what we need is another component here. Yeah, go ahead. Right. So the other component here is, we'll give it a name here in a moment, but every so often this generic sorting algorithm is going to have that conundrum. Here's A and B. Are they in order, are they out of order, or are they equal? And so what we're going to do, instead of deciding that for ourselves, we're going to hand that off to this other box over here. And it's going to return one of three things. Let me go ahead and... It's going to output an integer, which is going to be 0 if A is equal to B. It's going to return something negative if A comes before B. And it's going to return something positive if A is greater than B. All right. Does that sound familiar? Yeah. Think strings. What was the function for comparing strings? Yeah, strcmp, right? That it returns something negative if this string goes first. It returns something positive if this string comes later. and it returns 0 if they're the same string. Right? This thing is going to be called a comparator. Right? Now, to be able to start using this thing, we're going to have to model it in C. And to do that, let's go over here. What we need is function pointers. Okay. So we've already looked at pointers. Let me go ahead and, where's my notes here? Where's my function pointer notes? Okay, just one moment. Let me go ahead and grab something else here. Nope, that's not it. That's not from Spring. Here we go. I want this. Okay. All right. So if I've got a regular old integer here, x, right, and I can set it equal to 42, how do I create a pointer that can point to x? This is a good review, too. Make a pointer that can point to x. Right? So is it p? Nope. Int star p. And how do I make it point to x? Ampersand x. There we go. All right. So that's a regular old pointer. Oh, no, I shouldn't call it regular old pointer. I've been using that terminology for regular old variables. That is a variable pointer, a pointer that points to x. You can also create pointers that point to code, right? i.e. a function. Right? So does this make sense, first of all? Think about this pointer. What is it pointing to? It's pointing to a memory location. What's stored in memory? A bunch of numbers, right? Data. What else is stored in memory? Files are stored in memory, right? What else is stored in memory? Your code, right? Remember, how is your code loaded up? It's loaded up into this stack frame. There's your code right there. When main is called, a new stack frame for main is created. You call another function, you call another function, you call another function. But your code still lives down here. It's got to live somewhere, right? It's got to live in memory. So it makes sense that you can make a pointer. You can also create pointers that point to the memory location at which a function is stored. Okay? So let's go ahead and do that. Here's the syntax. Star ptr2 func, right? And double int char. There we go. This is a function pointer. It can point to any function that returns an integer and takes 3 variables: a double, an integer, and a character. Hey, isn't that convenient? I've got this function up here called foo that does exactly that. It returns an integer, it takes a double, it takes an integer, and it takes a character. And it ultimately ignores that character, and all it does is multiplies x and y together and returns the value here, truncated because, of course, it's an integer. Okay? Now, at that point, is that pointer pointing to anything in particular? ptr2 func points to question mark. What does it point to at that point in the code? Well, ask the same question for something that you're already familiar with. If I didn't already assign it, what does p point to right now? Garbage, nothing, who knows, right? So it points to nothing, garbage, right? Invalid memory location, etc. How do we get it to point to our foo function up here? Right? So let me go ahead and take ptr2 func and set it equal to what? How did I do it up here with a regular old variable? Here's my regular old function, ampersand foo, right? However, you can also just use the function's name. In other words, ptr2 func is equal to foo. Right? There we go. Now, some of you may remember, you may not remember, that you've created variables, for example, int x is equal to square root. There we go. And it compiled with a warning, but it didn't give you anything that you wanted, or anything that made sense, right? Do we now understand why? Maybe you didn't make this mistake. If you didn't, that's great, right? What am I doing here, though? Right? I'm failing to remember that I need to actually pass something in, 2.1, right, as an argument to that function. But now we understand why this might work, or it might even compile. Why? That's a memory location. If you don't have the parentheses here, that means that you are referring to the memory location of the function where it's stored in memory, which is why you can do something like this. But you shouldn't be doing something like this on line 27, right? Now that we have a pointer to the function, we can call it via its pointer. For example, int, did I already use x? Yeah. So int y is equal to ptr2func. And we'll go ahead and pass in, I don't know, 12.5 and 4. And then C. There we go. Printf y is equal to %e and the line. There. And let's go ahead and compile this. Oops, where I'm in the wrong directory. Where should I go? General. There we go. GCC func pointer demo. There we go. %d. I need to output y. There we go. All right. So what's this going to output? Let's predict. Pointer to func is going to pass it is a pointer to this foo function here, right? It's going to pass in 12.5, 4, and C. 12.5 and times 4 is 48, 49, 50, right? Truncation keeps it at 50. So my guess is that it's going to output 50. Hey, cool. Right? Well, that's kind of useless. Why didn't you just call foo, right? In other words, why didn't you just do this? Why not just call foo, right? That you can do something like this. Oops. You don't need a pointer to do that. You don't need something fancy. You can just call the function, right? Right? The answer is because function pointers allow you to pass functions to other functions. All right. Now, to understand that, how many people are in Calc 2? All right, 1, 2? Okay, not many. All right. For those that are in Calc 2, tell me how you would do numerical integration. Give me one of those rules where you've got a function and you want to compute the space under the function, right? It's an integral, right? So how do you do it numerically? Okay, you could do it symbolically, right? If you take the integral and then compute it from a to b, or what b minus a, right? You could do that, but what if it's not even integrable, right? It's some weird function that nobody knows the integral symbolic integration for. There we go, the trapezoid rule. What other rules are there? Riemann sums, which are just a bunch of rectangle rule, basically. What else? Simpson's rules, right? Et cetera, et cetera, et cetera, right? So now think about writing a Riemann sum function, right? You'd have to write a Riemann sum function for x squared. Oh, no, and now I want to integrate this other function over here, x cubed. Well, now I need to rewrite my code to do that. Now I have another function over here, and I need to rewrite my code to do that. I need to rewrite my code for every single time. What if I wrote one function that implemented Simpson's rule or Riemann sum or whatever, and I was able to give it the function that I wanted it to integrate? Right? What if I wanted symbolic pointers to math functions? Right? For example, let me go ahead and create another function pointer here. Double ptr to math. And I need a star here. There we go. And it takes a double. There we go. So at this point, what is ptr to math pointing to? Nothing. Let's make ptr to math point to the square root function. All right. There we go. And then let's go ahead and call that square root function through its pointer. I don't know, 2.0. What's the square root of 2.0? 1.41 something something something, right? So let's go ahead and capture that value, printf. Z is equal to percent f and the line z. There we go. Oops. Do I not have my math library? No, I have my math library. But I need to compile it with the math library, and it's happy. There we go. Sorry. Run that again. A dot out. There we go. 1.411 something something something. Right? I could have done that directly by simply calling the square root function, right? But what if I wanted a function to do all the work for me, right? So let me go ahead and run, write a function called run math, right? This run math will take an input, x, but it will also take a math function to run, right? Now, that's not real C. We're going to come back and fill that syntax in, right? So I'm telling this run math function, here's my input, x, and here's the function that I want you to run. Sometimes I want you to run square root. Sometimes I want you to run sine. Sometimes I want you to run cosine, right? How would it go about doing that? All it needs to do is run the function. Come on x and return the value. Right? There we go. Now, that was not real C. What do I need to do instead of saying that sometimes I want you to run that function, other times I want you to run that function, other times I want you to run that function? What am I doing in each one of these cases? A pointer to a function, right? A pointer to a function that returns a double and takes a single double. So let's go ahead and move that up there. There we go. And F, because that's what it is. F. Right? Now that looks super mathy to me, right? In fact, most mathematicians would just use f of x. Now you can imagine that if this is not just run math, but it's run Simpson's rule, right? And of course, now you're going to have to write a loop or control structure or something like that. But you don't know what it is. Is it the sine function? Is it the cosine function? Is it the square root function? Is it x squared, right? You just called it f because you were able to do this by simply passing in a function pointer instead. Right? So run math. There we go. And now I can do it down here. Run math, and I'm going to get an answer, z. Run math, and I want you to go ahead and run it on 2.0 and square root. There we go. And print out the result. We'll get the exact same result, but let's go ahead and run math again on sine. Run math again on cosine. What's the sine of 2 and what's the cosine of 2? Radians, remember? Does anybody know? I have no idea either. I'm going to assume that those are correct. Right? I was able to run arbitrary functions by passing it into another function. Now, granted, we're not really doing much other than just calling the function here. But what else could we do? We can run our sorting algorithm by saying, the sorting algorithm is here. I don't know how to order these. I know how to sort, right? I don't know how to order these things, though. But if you gave me a function that I could take these A and B and hand it off to a comparator, and it told me something negative, something positive, or 0, then I can go ahead and sort that for you. And I don't have to know what they are. They could be integers, it could be doubles, it could be books, it could be anything. Right? That's the beauty of function pointers. It allows me to do meta-programming, right? So unfortunately, they've abused the word Facebook turned into meta. What is the actual meaning of meta? Oh, yeah, okay, that's a good idea. That's a good way of putting it. Inception. It's like the movie Inception. Define meta. Right. Making or showing awareness of reference of oneself or the activity of taking place, especially in an ironic or comic way. Self-referential at a high level, right? In other words, I can write code that runs other code, right? It's meta programming. It's generic programming. This allows me to create one sorting algorithm, and I never have to write that sorting algorithm again. It applies to any type. All I need to do is write this comparator down here, right? I don't have to write the complex code of swapping stuff out and doing all that stuff, right? All I have to do is write, well, they go like this, or they're equal. Right? And that's all I need to do. Right? So let's do that by introducing a comparator function really quick here, and then we'll go ahead and end it and continue next time. A comparator function, right, has the following signature. Right? It's going to return an integer. Why? Because it returns something negative, positive, or 0, depending on the relative ordering of the two things. Right? It's going to have a generic name. Right? When you actually implement these things, you would give it a name like, I'm comparing integers in ascending order, or I'm comparing books by their last name, author name, or whatever, right? But for now, I'm just going to call it CMP, okay? And it's going to take two things. Well, can it take two integers, int x and int y? Does that look generic to you? No, it looks very, very specific. What's it going to apply? What are x and y? It only works for integers, okay? We're going to go ahead and make them into pointers instead, because that's the C way. But is that generic? Nope, because I'm pointing to two specific things, that integer and that integer, okay? So I'm going to go ahead and take away this integer. Right? I could make it into a double, but that's just more specific in a different way. What is a generic pointer? Yeah. Void. We've seen this before. Where? Malloc. Malloc returns a generic void pointer. You can do with it whatever you want, right? You can change it into an integer. You can change it into a double. You can change it into a book, right? I'm not going to be making changes to it either, so there's my promise. Whatever you give me, I don't care what they are, right? I don't know what they are, right? They're just going to be x and y, but I'm not going to change them, right? I'm simply going to look at them and say, it goes like this, or this, and that's it. That's the signature of a comparator. That allows me to use a Q-sort algorithm. Q-sort. What do you think Q-sort stands for? Quick sort, because it's quick, right? Exactly. Now, it doesn't have to be a quick sort implementation. In fact, most modern implementations are some sort of a modified merge sort, but because we're living with, they called it Q-sort because it was quick sort 40, 50 years ago. We're stuck with the name nowadays, right? By all rights, it should just be called sort, right? Because we don't care what algorithm you're running under the hood. We just want you to sort it, right? Q-sort. Now, to sort something, of course, you still need to give it an array, the size of the array, something else, and your comparator, CMP, right? That's where a function pointer comes in. I want you to use that comparator function over there. Oh, now I'm sorting something different. I want you to use that comparator function over there, right? Or whatever. This other thing over here is the size of whatever you're trying to sort, right? Because if it doesn't know what these things are, how is it going to swap them? This thing could be an integer, which is 4 bytes, and this is an integer, which is 4 bytes, and so it needs to swap those 4 bytes. It could be a double, which is 8 bytes and 8 bytes. Now it needs to swap these 8 bytes with those 8 bytes. It could be a book with 40 bytes, in which case it needs to swap this 40 bytes and this 40 bytes. You need to tell it that. Whatever you're sorting, you need to tell it how many bytes it is. But otherwise, you just give it the array, the number of elements in the array, the size in bytes that each element takes, and the comparator that you want to use. We'll go ahead and pick it up there on Thursday. Right? Yeah. It's very polymorphic, and all that stuff would fall under polymorphism. Operator overloading is a little bit different, though. It has to do with typing and generic programming, rather than because there's not really an operator here to overload. You're basically erasing the type in order to give it to a generic function, and instead of making that function adapt to you.